Dear students, welcome to Easy BTech, your guide for BTech and beyond. We are discussing the subject Signals and Systems, and in this subject today we are going to discuss properties of Fourier transform. Very important concept. Before going to our concept, please subscribe, share the channel. This channel is very helpful to you. So all of you follow the channel, follow videos regularly. Let's start our today's session. Properties of Fourier transform, very important. So we discuss properties of Fourier transform. They are very important. So today's topic, properties of Fourier transform. And we have discussion about properties of Fourier transform. Means we discuss the statement or definition of each property, and at the same time we will do proof of that taken property. So properties of Fourier transform. Properties of Fourier transform. So for examination, very important topic it is. So in the exam they will ask you at least two properties from Fourier transform. So please listen. Very simple. So the first property, linearity property. The first one is linearity property. Linearity property. Linearity property. So actually the Fourier transform pair is denoted as Fourier transform pair is denoted as so this is a way of writing Fourier transform pair. Suppose x of t is the signal, its Fourier transform is capital X of omega. Okay, this is the Fourier transform pair representation or denoted like this. So now we are going to discuss linearity property. What is linearity property is, if x1 of t Fourier transform is capital X1 of omega, x2 of t Fourier transform is capital X2 of omega, capital X2 of omega, then the linear combination of x1 and x2, Fourier transform of linear combination of x1 and x2, that is a x1 of t plus b x2 of t, a x1 of t plus b x2 of t. For this combination, this is linear combination of x1 of t, x2 of t. So for this combination, what will be the Fourier transform? So the Fourier transform is a x1 of omega plus b x2 of omega. Right? So let's see the proof. So each property we can do proof with the help of Fourier transform definition or Fourier transform formula. Just if you understand the Fourier transform formula, using that formula we can have proof for all the properties. All properties are proved with the help of Fourier transform formula. Right? So very simple. So we know Fourier transform of x of t. Fourier transform of a signal x of t is capital X of omega is equal to integral minus infinite plus infinite x of t into e to the power minus j omega t, dt. So this is the Fourier transform of a signal x of t. So here the signal is x of t, therefore x of t will appear in integration. Suppose Fourier transform of y of t, so here integral minus infinite plus infinite y of t into e power minus j omega t. So whatever the signal we have, x of t or y of t or x1 plus x2, whatever the signal we have, that is taken here. Whatever the signal you have, that is written here in the integral. So that is a matter here, that is a point here. So we want Fourier transform of linear combination of x1 of t, a into x1 of t plus b into x2 of t. So now Fourier transform of a into x1 of t plus b into x2 of t. So how to write this Fourier transform? So whatever the signal, that will be in the place of x of t. Here the signal is ax1 plus bx2. So take that total. So integral minus infinite plus infinite. Whatever the signal we are taking, whatever the signal here, ax1 of t plus bx2 of t. So this is the signal into e to the power minus j omega t dt. So if you understand this step, remaining is simple. So here we have plus, and here we have ax1 and bx2. So separate, we get the answer. So a can be written outside. We can write a outside. Integral minus infinite plus infinite x1 of t into, and here e power minus j omega t. So I am taking minus j omega t dt plus b also you can take outside the integral minus infinite plus infinite x2 of t e to the power minus j omega t dt. Now if you observe these two integrals, integral minus infinite plus infinite x1 of t power minus j omega t, it is a Fourier transform, right or not? Compare these two integrals and this integral, like Fourier transform formula, right or not? So the answer is now a. This is the Fourier transform of x1 of t, therefore capital X1 of omega, plus b, and this is the Fourier transform of x2 of t, therefore capital X2 of omega. Very, very simple proof. So only formula, Fourier transform formula, if you know and if you understand it well, you can do proofs easily. So this is the linearity property, first one, right? Similarly, we go to second one, the second property, time shifting property. The second property is time shifting property. Time shifting property. So first we see the definition, then we do the proof. So every property, definition plus proof, because Fourier transform properties are very, very important. So now see the definition. If x of t Fourier transform is x of omega, capital X of omega, then time shifting means x of t minus t naught. What is the Fourier transform of x of t minus t naught? That is the second line. So the answer is capital X of omega into e to the power minus j omega t naught. So x of omega is multiplied by exponential e power minus j omega t naught. Let's see the proof again. So I said you already, I told you, proof is Fourier transform formula, from Fourier transform formula. So we know Fourier transform of x of t. Fourier transform of x of t is x of omega is equal to integral minus infinite plus infinite x of t into e to the power minus j omega t dt. Okay, so we take the x of t minus t naught Fourier transform. So how to write Fourier transform of x of t minus t naught? So how to write it? It doesn't mean that t is equal to t minus t naught. Don't write in the place of t is t minus t is t minus t naught. We want Fourier transform of x of t minus t naught. This is the signal. So how to write? Integral minus infinite plus infinite. Here whatever the signal we have, that we take. So x of t minus t naught into e to the power minus j omega t dt. That's all. E to the power minus j omega t dt. So here the bracket t minus t naught, I am going to take it as, let t minus t naught is equal to the variable p. The t minus t naught I am taking as p. Means I am going to convert t as p. I am going to write t in terms of p. So t minus t naught equal to p. Therefore t will become p plus t naught. So minus t naught, just I am sending right side. And discuss about lower and upper limits. So dt, what happens to dt? Dt will become dp. Here t naught is a constant, so 0. So dt is equal to dp. And what about lower and upper limits? The lower limit. So p is equal to, we have t minus t naught. So what is the t lower limit here? T, the lower limit is minus infinity. So p is equal to minus infinite minus t naught. So minus infinity minus t naught, it will be minus infinity only, right? And upper limit, if you see upper limit, so here t upper limit is infinity. So p is equal to t minus t naught. So what is the upper limit of t? T upper limit is plus infinity minus t naught. So from infinity, if you subtract t naught, it is infinity only, right or not? Infinity is a large value. Then go to substitution of all these in the above integral. So we are going to substitute all these in the above integral. Then we can see changes. So is equal Fourier transform of t minus t naught. X of t minus t naught is, lower limit is minus infinite, upper limit is plus infinite. X of p minus t naught, t minus t naught is p into e to the power minus j omega t. What is t here? P plus t naught. So write p plus t naught. Dt, what is dt here? Dp. So take dp. Okay, so now the integration is with respect to p. Integration is with respect to p. So only p terms we keep inside, the remaining will take outside the integral. So the remaining means e power minus j omega and t naught. These two are written outside. That term e power minus j omega t naught is written outside. Then integral minus infinite plus infinite x of p e to the power minus j omega p dp. This is we have. And if you observe this integral clearly, the integral is like Fourier transform formula in the same way or in the same manner, right or not? Just observe the Fourier transform formula and this integral what we have. Just p, in the place of t we have p, everything is same. So therefore the integral is taken as Fourier transform formula x of omega into the exponential e power minus j omega t naught is as usual. Okay, right? So here I want to mention one point about spectrum, magnitude spectrum. So the magnitude spectrum of x of t magnitude spectrum is magnitude of x of omega, and the magnitude spectrum of time shifting of x of t, that is x of t minus t naught, is also the magnitude of e power minus j omega t naught. So this magnitude e power minus j omega t naught cos theta minus j sin theta, magnitude will become 1. So finally we get same x of omega. So time shifting will not change the magnitude spectrum of this signal, right or not? The time shifting will not alter or change the magnitude spectrum of the signal. Time shifting not changes magnitude spectrum. So this is the point. Okay. Suppose if we have here x of t plus t naught. So minus t naught indicates right shift. Signal is shifted right side. Then the spectrum x of omega is get multiplied by e power minus j omega t naught. Suppose if you have t plus t naught, left shift, t plus t naught. So I am using black color. If x of t plus t naught, its Fourier transform will become, what happens? X of omega into, I am writing here. So the answer is x of omega into e to the power plus j omega t naught. So here if you have plus in exponential also plus. If you have minus in exponential also minus. That's all. This is the time shifting. And third one, very important, time scaling. The third property is time scaling. Time scaling. So first we see the definition, then we go for proof. If x of t Fourier transform is x of omega, then time shifting means x of at, sorry, time scaling. X of at is what? The Fourier transform of x of at is how much? So this will be 1 by mod a x of omega by a. 1 by mod a x of omega by a. And in this property we can understand that compression in this property we can understand, point. If the signal is compressed in time domain, it will be expanded in frequency domain. So compression in time domain is equal to expansion in frequency domain. Compression in time domain is equal to expansion in frequency domain. Expansion in frequency domain, and vice versa. Vice versa means if the signal is compressed in frequency domain, the signal is expanded in time domain. So this is vice versa. Okay, so this is the point here. If the signal is compressed in time domain, it will be expanded in frequency domain. If the signal is compressed in frequency domain, expanded in time domain. So that point we can have in this property. That information is there in this property. Let's go to proof. We have proof now. So again we write the Fourier transform formula. So Fourier transform of a signal x of t is equal to x of omega is equal to integral minus infinite plus infinite x of t e power minus j omega t dt. Right? So this is the Fourier transform formula, simple. Then we want Fourier transform of x of at. What is the Fourier transform of x of at? So it doesn't mean that t is equal to at. Don't understand like that. So the signal is now x of at. This is the signal. So how to write this Fourier transform? Integral minus infinite plus infinite. Here x of at in the place of signal x of t, we have x of at. So take that x of at and remaining e power minus j omega t dt, the same. It will be same. Let's simplify this like previously. So here the bracket at is there. So let at is equal to p, the variable p. From this t will become p by a, p divided by a, and lower and upper limits, and we can also discuss dt. dt will become dp by a, and lower limit, upper limit, all we can discuss. Lower limit, so p is equal to, what is the p? At. So what is the lower limit of t? Lower limit of t is infinity, minus infinity, therefore it will become minus infinity. Upper limit, if you take upper limit, so we have p is equal to at, upper limit of t plus infinity, therefore plus infinity into a, it will become plus infinity. So this total information we are going to substitute in the above integral. This total is going to substitute in the above integral. Now the integral will become, lower limit is same, minus infinite, upper limit is plus infinite, x of p into e to the power minus j omega. What is the t? T is equal to p by a, so take that to p by a. And what is dt? dp by a, so take dp by a. So this 1 by a we can write outside the integral, so 1 by a, and integral minus infinite plus infinite, integral minus infinite plus infinite, x of p e to the power minus j omega by a. So here p by a I am writing omega by a, both are same, p dp, right? This is the integral we have. After at equal to p, this we have. Now this integral again compared with our Fourier transform formula, just to do comparison, we can get the clarity. So comparison of these two. So by comparing these two, what we can understand, the formula is almost, both are same, but except in the place of omega we have omega by a. So here we have omega, that is why it is x of omega, understand? But here we have omega by a, therefore what is the result? 1 by a x of omega by a, right? After comparison, okay. Now suppose here the right side we have 1 by mod a, means here always positive, a is positive. Now the case is, I am taking if a is equal to negative, like minus 2 or minus 3, something negative value, negative real value. So what will be the answer? If a is less than 0, negative, a is negative value, then what is the Fourier transform of x of at? What is the Fourier transform of x of at? We get 1 by a x of omega by a. So here a is negative. For example, let's take a is equal to minus 2. Example, it is a value less than 0. I am taking minus 2. So 1 by 2 you get here, not minus 2. So that is the meaning of mod here. So outside we get 1 by mod a. 1 by mod minus 2, it will become plus 2. 1 by 2. So I am writing 1 by 2, right? Omega by minus 2, or minus x of minus omega by 2. So this is the way here we have, okay, right? So compressed, if the signal is compressed in time domain, it will be expanded in frequency domain, right? Omega by a. So here into a into t, here omega by a, that is a statement it is saying, that information is there, clear? Now we are going to discuss time reversal, the next property, time reversal. Time reversal. So this time reversal we can do using time scaling property. with the help of time scaling property we can prove it. So first write the definition or statement. If x of t Fourier transform is, what is x of t Fourier transform? X of omega. What is the time reversal? X of minus t means time reversal of x of t, folding of x of t. What will be the answer? X of minus omega. Okay, see the proof. This proof we can do using time scaling property. So this we can do using time scaling property. So let's take that time scaling property, then we can do the proof. Just 1-2 lines. So what is the time scaling property saying? Fourier transform of x of at is 1 by mod a x of omega by a. So for x of minus t, x of minus t means what is the a value here? A value is minus 1, that's all, simple. So what is the answer now? 1 by mod minus 1 x of omega by minus 1. So 1 by, here mod minus 1 is 1, so no need to write 1 by 1. So x of minus omega. So this is the proof. Very simple. Okay, very easy. So till now we have discussed 4 properties: linearity, time shifting, time scaling, time reversal. Further we have properties like frequency shifting, okay, time integration, time differentiation, convolution, right? So we have properties further that we can discuss in the next session. Thank you, students.